Hello everyone, welcome to my presentation. My name is Yutong Zhao, and the title of my presentation is Towards Optimal SABR Margins in Prostate Radiotherapy, which is my master's project. And here is the co-worker and supervisors of this project. They are Martin, David, Simon, Pejman, and Shahin. So before we start, allow me to give you a simple introduction. The prostate cancer tumor is one of the late reacting tissue, which means that most of radiotherapy prescriptions prefer having a low number of fraction number and large fraction size. And it is the reason why SBRT, or the SABR, is very suitable for prostate cancer treatment. Many studies have demonstrated excellent efficacy of SBRT for low-risk and intermediate-risk prostate cancer. However, late fraction size also means higher possibility of having more serious side effects after accepting the treatment. The side effects like radiation proctitis or the lymphedema could result in a lowering of patients' living quality after accepting the treatment. So why there is side effects in the radiotherapy? That mostly because organ at risk OARs are not stationary during the treatment. So the OAR's motion will contribute to the uncertainties in the radiotherapy, and that will lead to the radiation to the OARs, and finally it will result in the side effects after patients having the radiotherapy. So the best solution is create a PRV margin which could cover possible OAR's motion, and so in this way we could put uncertainties in our consideration when we were creating the treatment plan. And so we could protect the OARs from unnecessary radiation, and finally we could improve the treatment outcome. So the aims of this research are very simple. Our first aim is to developing a concise and effective PRV margin generating recipe which could make allowances for bladder and rectum interfraction motion in prostate SBRT. Our second aim is generating bladder and rectum PRV margins in coordinates with this recipe. The margins aimed to cover at least 90% of bladder and rectum wall outward displacement, which is the wall displacement promoted by organ volume expanding for 90% of prostate cancer patients. The idea of planning organ at risk volume, which is PRV, was addressed by ICRU Report 62. It is created to accommodate the uncertainties caused by OAR motion. And the next is the materials has been used in this project. The delineation of organs was undertaken with the MIM software, and for this project, 16 prostate cancer patients were selected randomly from Genesis Cancer Care database. For each of the patients, information includes 1 planning CT scan and 5 pre-fraction CBCT scans. All CT scans covered both the abdomen and the pelvis from above the bladder to the axial tuberosity, while the CBCT scans only cover the pelvic region from the top of the bladder to the anus. In this project, we delineate all the bladder and rectum for every patient, so there are 15 patients CBCT bladder contours are qualified, and the rectum contours of 13 patients are qualified for the project. For the sake of measuring the organ wall interfraction displacement, the measurement of organ motion was conducted by following 3 steps. First, for each patient, the organ contours from 5 CBCT image sites were transferred to the CT image using fiducial marker-based regrade image fusion. And then, for each OAR, we define a Brownian union contour which describes the union of contours from all 5 fractions. And finally, the biggest organ wall outward displacement was evaluated through measuring the distance from the CT contour to the organ union contour. For each of the patients, we measured the largest wall outward displacement in 5 directions for bladder and 4 directions for the rectum, and we analyzed this displacement on the transverse slices of PTV, usually going to be 15 to 20 slices. The organ wall position distribution was also measured. First, we select the 3 transverse plans for the top, middle, and bottom of the bladder and rectum separately, and then we set a coordinate system on it. And third, on each plan and every direction, the distance from the CT organ wall, which is the yellow contour over here, to every 5 fraction CBCT organ walls, which is this pink contours over here, were measured individually. The distance values were normalized by the first distance value. Next, the histogram of wall position distribution will be generated, and here is an example. The x-axis stands for the percentage of maximum distance, and the y-axis stands for the number or the frequency. When x equal to 0, that means the CT organ position, and when x equal to 1, that means the furthest CBCT organ wall position. Based on the histogram, we can calculate the distance range from the CT organ position, which represents 90% possibility interval, which is the area occupies 90% of entire histogram area. This research used symbol K to represent such a distance value. Our PRV margin generating recipe are basically following the formulas over here. So first, for one direction D and patient P, the biggest organ wall outward displacement values in each sample slices D are all summed and divided with the total sample slice number n to calculate the average value. In this example, the average value is over here, and then the margin width W that covers 90% organ wall outward motion for patient P is generated by multiplying K value and the D value. In here, we assume that the K value equal to 0.8, so we can multiply in the values in the list B with the 0.8 to generate the list C. In the next step, the patients are ranked in each direction according to their W values from the largest one to the smallest one. And finally, the 90th percentile value is picked up for all directions to create the PRV margin. The position of the value Q is given by formula over here. So in this example, the Q value is going to be 1.6, which is approximately equal to 2. So we're going to pick the second value over here to be our margin width. Unlike the bladder with a spherical shaped geometry, rectum has a tubular geometry. This geometrical shape and the complexity of surrounding organs result in the complex rectum wall displacement and no uniform motion. For example, the superior part of the rectum usually sees a larger wall displacement compared with the lower part of rectum. So, before we give in rectum PRV, we better segment rectum first. In this study, the rectum was first segmented into cranial half and the caudal half of the rectum, according to the position of the rectum flexure over here. And then the cranial half of the rectum was divided into the superior and middle part of the rectum according to the position of the midline over here. And the resulting structure was named as superior, middle, and lower part of the rectum. After generated PRV margins, we designed 3 parameters to help us validate and compare the performance of the PRV margins. The first one is called original coverage, which is equal to the percentage of CBCT ballooning union volume with the CT organ volume relative to the union volume. The second one is called effectiveness, which represents the percentage of useful PRV margin volume account for the entire PRV margin volume. The useful PRV margin volume means the PRV margin volume which could cover organ motion as indicated by all CBCT image for each patient. The third one is called outward coverage, which stands for the percentage of outward organ motion area that could be covered by this PRV margin. The PRV outward coverage would be calculated for all patients to get the 10th percentile value for each of the PRV margin. The PRV margin would be considered as qualified only if the 10th percentile value larger or equal to the K value. 2 histograms here show the result of bladder and rectum wall position distribution. We assume both distributions are normal distributions, and then we calculate the mean value, which both approximately equal to 0.5 as standard deviation approximately equal to 0.2. And next, we calculate the K value, which is 0.77. And here is the result of bladder PRV margins. The PRV1 was generated to cover at least 90% of bladder outward motion for 90% of all patients. PRV2 was generated with the same criteria through only considering patients whose bladder volumes increased by less than 20% of the baseline bladder volume throughout the treatment course. The size of the 2 PRV margins are listed over here, and they all passed our validation process. For the sake of proving the necessity of segment rectum, 2 rectum PRV margins, one ordinary and one combination with a similar margin volume, were created for the comparison. The combination margin was produced by combining 3 PRV margins corresponding to 3 different rectum parts which defined by our rectum segmentation method, while the ordinary margin is a spatially uniform margin which was generated by following our recipe with treating the entire rectum as a whole, and here shows their sizes. On the aspect of effectiveness, the result shows that under the approximately equalized margin volume, the effectiveness values of combination margin for 9 patients are larger than that of ordinary margin. The maximum increment is 10%, the average increment is 5%. For the rest of 4 patients, the effectiveness values of combination margins are smaller than that of ordinary margins, but the maximum reduction is only 1.71%. On the aspect of the outward coverage, the combination margin could improve outward coverage value for 85% patients, and except patient 1 and patient 4, it could increase maximum 14%, minimum 0.6%, and average 7% of outward coverage value. If we rank all the patients according to the value of the original coverage, it could show that the improvement of outward coverage value by applying combination margin could be increased as the patient's original coverage value decreases, which means the combination margin could greatly increase the outward coverage value for patients who experienced a relatively huge rectum wall displacement. Approving using combination PRV margin is a better option for the rectum. A new combination PRV margin was generated, and the size shows over here, and it passed our validation process. And of course, there are many errors exist in this project. The first one is contouring error, which results from low CBCT image resolution. The second one is measurement error, which produced by manually measurement procedure. And the third one is image fusion error, which caused by the position shift of fiducial markers among the different CBCT or CT fractions. And thanks everyone for listening.